So in this lecture, I am going to discuss about the important topics in electrochemistry. We will discuss more about the oxidation reduction reactions and equations. What are the fundamentals in electrochemistry? I will try to cover in this lecture. As you all know, that electrochemistry is all about the electron transfer reactions, whether it is spontaneous or non-spontaneous. So today you can classify into two types. One is spontaneous reactions that involve the electron transfer. It can generate the electricity. For instance, it can be a battery or voltaic cells. There are certain non-spontaneous reactions that can also involve electron transfer. But since when you say non-spontaneous, then it should be forced to proceed by the addition of an electric current. So you supply some electric current, you force the system to do some reaction, whether oxidation or reduction, and that process, entire process is electrolysis. A simple example is water electrolysis. You supply potential in the form of like higher than the overpotential. The modeling potential is 1.3 volts, so you have to supply higher than the thermodynamic potential to minimize the you know minimize the reaction time and also to drive the electron to run that reaction, and specifically the activation energy barrier you have to minimize. For that you have to supply higher over potential. So that entire process is called electrolysis. Okay, so the electron transfer reaction can be of two types. One is oxidation, other one is reduction. Oxidation happens at the anode and reduction happens at the cathode. And together, all together, you can call the oxidation reduction reaction as redox reaction. Therefore, the field of chemistry that deals with oxidation reduction reactions or the spontaneous and non-spontaneous electron transfer processes, that is called electrochemistry. In other words, you can say that a study of intraconversion of chemical energy to electrical energy and vice versa. For example, electrical energy to chemical energy, like in the case of electrolysis cell, and the other way in the case of battery, where the charge will be stored due to the chemical reaction. Now, this textbook stuff, you already know that what is oxidation. The terminologies I want to briefly introduce to you, like oxidation, loss of electron by a species, and it leads whenever a species loses electron, it increases the oxidation number increases proportionally. When one electron is lost, then one positive charge will be increased, and if it is two, then two positive charge. So increase in oxygen. In other words, you can also say reduction means gain of electron or gain of hydrogen or increase in hydrogen amount. And when a species gains an electron, the oxidation number decreases. For instance, you are having like oxygen 2 minus, you add one electron, it becomes oxygen minus. And similarly, if you are taking a chloride anion, like Cl minus, you add one electron, it becomes the chloride electron. So that's simple. So oxidizing agent is something an electron acceptor that species will be reduced. Reducing agent is an electron donor that species will be oxidized. In simple words, you can say Leo, loss of electron, that is called oxidation. Okay, simple oxidation reduction reaction. So you might wonder why copper becomes blue. For example, you take a copper wire, hang it in a solution, then you dip it in silver nitrate solution. The solution turns blue. Initially it was white, but when you drop a copper wire or hang it, the copper wire in a silver nitrate solution, it becomes blue. What is the reason? So that simple displacement reaction occurs. So oxidation and reducing agents in direct contact. For instance, copper will be the copper wire. The copper present in the copper wire will be oxidized to copper 2+, which means it loses 2 electrons. And silver ions in the solution will gain that 2 electrons and become silver neutral. So what will happen when a metal rod of magnesium or zinc or aluminum, any metal, any when soaked in copper sulfate, it forms copper, copper deposits will be formed and magnesium ion will be formed. Initially, the copper sulfate solution will be blue, but once immerse a magnesium rod or a plate or a foil, whatever you name it, then it becomes brown in color. Similarly, when aluminum rod or a foil or a plate is immersed in copper sulfate, it becomes in blue color, and then the aluminum sulfate, it will become slowly the turbid white precipitation that you can observe. These are all due to some electrochemical oxidation reduction reactions that is called galvanic displacement reactions. Okay, now we move on to the electrolyte. So what do you mean by electrolyte? So any substance that conducts electricity by producing freely moving ions. The more the number of freely moving ions, the higher the electrolyte conductivity will be. So when you dissolve in a solvent, like any freely moving ions are present more in a solvent such as water or in the molten state, that is called electrolyte. Examples includes NaCl, PbBr2, NH4PF6, N tetrabutane, amine like NBU4, N hexafluorophosphate, any like hexafluorophosphate is a salt, and also it can be butyl, tetrabutyl ammonium hexafluorophosphate. You can take it and you can use it dissolve in water, and you can use it as a water. Mostly it is a non-aqueous salt, so it organic salt, so it will not be dissolved in water. Especially these two salts, hexafluoroammonium, uh, hexafluorophosphate, or instead of ammonium you can have it's a tetrabutyl. So that you can dissolve in the acetonitrile instead of water. NaCl, as you know, you can dissolve in the aqueous. So when you dissolve in aqueous electrolyte, that is called aqueous electrolyte, and when you dissolve this in acetonitrile non-aqueous solvent, that is called non-aqueous electrolyte. So other than aqueous and non-aqueous electrolyte, there are other two types called strong electrolytes and weak electrolytes. We will discuss in detail. What do you mean by strong electrolyte? When an electrolyte dissociates completely and exists as ions in the solution, then you can call it as strong electrolyte. Then ionic compounds are typically strong electrolytes. Strong acids, strong base, and their salts. All are strong, like HCl and its salt, sodium chloride. Here I have given an example, HCl. You drop HCl in water, it forms hydronium ion and chloride ion. When you add, when NaCl is dissolved in water, it forms Na plus and Cl. There, instantly, ionization will happen. That's why they are called as strong electrolytes. They are good conductors because they dissociate well and produce many ions in solution. They conduct electricity in molten or in aqueous solution. Example, I have already given this one. Weak electrolyte, a weak electrolyte partially dissociates in solution and produces relatively fewer ions exist in water as a mixture of individual ions and molecules. Similarly, weak acids and weak bases are formed via weak electrolyte. For instance, if you dissolve acetic acid in water, you form acetate. Acetic acid is a weak electrolyte or a weak acid. Similarly, ammonia is a weak base, and if you dissolve in water, it forms ammonium ion. They do not conduct electricity as good as the strong acids or strong bases. That's why they are called as weak electrolytes. Ammonium phosphates are also the other example. So the electrochemical cells. Now after the electrolyte, we move on to the electrochemical cells. So these are the devices which convert electrical energy into chemical energy, or vice versa. So it is a device or a system in which electrical energy is converted into chemical energy. So based on the activity taking place in them, you can call it as, or you can categorize them into two major categories. One is electrolytic cell and the other one is galvanic cell. We should understand the basic difference between these two. For instance, in an electrolytic cell, always chemical changes occur when you supply the electrical energy. So you supply the electrical energies and you initiate some chemical changes. For example, you supply electrical energy, initiate the water dissociation process, you split water into hydrogen and oxygen. That splitting is done with the help of electrical energy, so that is called electrolytic cell. Whereas galvanic cells are also called as voltaic cells. So here the electrical energy is generated on account of the chemical reactions occurring in them. It can be like chemical cell or concentration cell. So we should understand the basic difference between the galvanic or voltaic cell and the electrolytic cell. For that, the energy is supplied in the form of either current or potential. So we need to understand the terminology called oxidation potential, reduction potential, and standard electrode potential. Oxidation potential means from the name you can say that it occurs at the anode. Oxidation occurs at the anode. As a result, if oxidation occurs at the electrode at an equilibrium, the potential of the electrode can be termed as oxidation potential. Zinc is a classical example. Zinc acts as an anode where zinc oxidation happens and two electron process, zinc ion would be formed. Similarly, reduction process, the it can also occur the other way where zinc ion can accept two electrons and it can be reduced to zinc, zinc atom or a zinc metal. So zinc electrode can act as an anode as well as a cathode depending on the electrode potential of the cathode which you are coupling with. If you that we will discuss later. Okay? I don't want to go further in detail about that. We will discuss in the upcoming slides. Standard electrode potential is E0, which is nothing but if you measure oxidation or reduction potential at standard condition, which is nothing but 1 atmospheric pressure and room temperature 25 degrees Celsius, 293 Kelvin. The standard condition when you are measuring an oxidation potential or reduction potential, then you can call it as standard electrode potential. Now, this is one of the important concept which you should understand, that is salt bridge. So salt bridge is nothing but an inverted U-tube which contains a concentrated solution of inert electrolytes. An inert electrolyte is one whose ions are neither involved in any electrochemical chain nor do they react chemically with the electrolytes in two half cells. You have two half cells, you connect them with an inverted tube, and inside the inverted tube you take a concentrated solution of inert electrolyte like KCl, potassium chloride. The examples include potassium chloride, potassium nitrate, ammonium nitrate, any concentrated solution you can take, 1 molar, 2 molar, saturated KCl you can take, and you can form the salt bridge. Um, you can connect these two, which means the two solutions in the two half cells are not connected directly, but they are connected to through this salt bridge, where the salt which you are taking in the inverted tube remains stable and it will not take part in the reaction. What are the functions of salt bridge? So you can also use agar gel can be used inside the salt bridge as well, other than the salts. Okay? Um, and it connects the solution of two half cells, complete the cell circuit, and it prevents diffusion or mechanical flow of solution from one half cell to the other because they are not directly in contact with solution in the two half cell. The main point to note is it minimizes the liquid-liquid junction potential. So liquid-liquid junction potential can lead to the potential drop or the higher drop. So you have to use a liquid-liquid junction potential. You minimize the liquid-liquid junction potential by using a salt bridge. Another way you can also use a lugging capillary. That is the other way to minimize the liquid junction potential. We will talk later, or to minimize the voltage drop or ohmic drop. Okay, construction of galvanic cell or dimming cell. This is one of the important questions. They will ask you on the 8th mark. They will ask you to draw the diagram. It's a very simple construct of two half cell with two beakers connect with the salt bridge. Salt bridge you can take KCl, agar-agar or cotton flux you can have, zinc at the anode and copper at the cathode. You can connect both the electrodes to a voltmeter. Anode anodic oxidation will happen, cathodic reduction will happen, and you can have the electrolyte zinc sulfate on the left for the anode and copper sulfate. You can serve the copper cathode, and the concentration can be 1 molar, or depending on the concentration, you can also construct the concentration cell. So the reaction is very spontaneous. zinc anode oxidation will happen, zinc ions will be formed, and here it will release the electron which will go through the external circuit and it will reach the cathode where the copper will accept the two electrons and it will be reduced to copper. So these are the Hofstad reaction, zinc oxidation or zinc anode, how it oxidizes and releases the electron, copper, how it accepts the electron and it reduces. This is the net reaction. So it will be other way, Cu2 plus 2 electron giving Cu. That will be the cathodic reaction. The overall net reaction will be zinc metal plus copper aqueous Cu2 plus ion. It forms Zn2 plus copper. So galvanic cells, this is the diagram. You have to calculate the cell potential. As you know that you can calculate the EMF of the cell. This is very important. The difference in electrical potential. So this electrical potential difference only drives the electron from zinc to cathode, anode and cathode. Cell voltage or EMF and cell potential. The cathode is positive and the negative in the electrolytic cell. This difference also. The cathode in the galvanic cell is positive, cathode in the electrolytic cell is negative. So E naught cell is equal to E oxidation plus E naught reduction, or you can say E naught cathode minus E naught anode. Okay, either reduction or oxidation. You can use any one term, and you can calculate the EMF of the cell 1 mole. How? Because you can write the cell reaction, half cell reaction, or the cell net cell reaction. You can write zinc, uh, the electrode separated by Zn2 plus, and you have the salt bridge Cu2 plus and Cu. This will be the net reaction, and 1 molar concentration of copper and zinc will be 1 molar, same concentration, and the cell voltage will be 1.1. Why? The potential of zinc is minus 0.76 and copper is plus 0.34. So the net voltage will be 1.1. This is it. Standard electrode potential. When you talk about the standard electrode potential in electrochemistry, it is defined as the measurement or the measure of the individual potential of a reversible electrode at a standard condition standard state with ions. The concentration should be 1 mole or 1 mole per dm cube at a pressure of 180 and at room temperature 298 Kelvin. And you need a why we need a reference electrode like standard hydrogen electrode or a reversible hydrogen electrode. General practice, we call it as standard hydrogen electrode. As a key, it is a redox electrode which forms the basis of thermodynamic scale of the oxidation reduction potential. To form the basis of comparison with all other electrode reactions, hydrogen standard electrode potential is considered as zero and it remains zero at any equilibrium. It is very stable one and potential of any other electrodes keep changing or it is compared with that of the standard hydrogen electrode. For instance, the standard hydrogen electrode involves this hydrogen evolution reaction where two protons and two electron transfer process leads to hydrogen evolution. The potential for this one is zero. The standard reduction potential, how we can calculate for zinc and copper. For zinc it is minus 0.76 volt, for copper it is 0.34. The standard reduction potential of zinc and copper. You can calculate the potential of the Daniell cell. You write the half cell reaction at the anode, half cell reaction at the cathode, and you apply the potential like E naught cathode minus E naught anode. So cathode is copper 0.34 minus of minus 0.76, which will be 1.1 volt will be electrode setup. Okay, electrochemical series is very important. Like we need to understand how the potential or how the each elements or the uh, arranged based on the potential that is um, like 3.0 volt is the maximum negative potential standard reduction potential of lithium. But look at the middle one, this is hydrogen. So this is arranged based on the comparing with the standard hydrogen electrode that is 0 which remains constant, and comparing that we can uh, arrange from lithium to lead as well as from tin to this peroxide, the anode side, and this is for cathode. And also the lower position of the ion in the electrochemical series. It can also tell something about the oxidation strength or something like that. Uh, Like you can also not only for the galvanic cell, you can calculate the standard EMF of a cell for the magnesium copper system, and you, as I told before, write the half cell reaction, write the standard reduction potential, apply the E cathode minus E anode, and then you will get the 2.7 volt, and net reaction also have to write. And there are other types of cell called concentration cell. It is also a galvanic cell. In both electrode contains same material copper. Here, look at here, both anode and cathode are copper, but the concentration of the two half cells are different, zero point 0.1 and 1. So this type of cells, concentration difference is there, so it is called as concentration cell. Similarly, copper here also there, salvage, everything is same. If you have the same concentration, the net cell voltage is zero or the unit is zero. Here, the difference between the concentration leads to change in the voltage. So you can, this type of cell is called concentration cell. EMF of the cell and free energy exchange are very important. For spontaneous reaction, E cell must be positive. Here, you know that free energy is delta G, and it is related to the, this expression is very, very important. Standard electrode potential minus NFE, or if we say standard free energy gives free energy delta G naught, that is equal to minus NFE naught. One of the very important equation or expression in electrochemistry. This we can apply in Nernst equation, and this is nothing but minus RT log K, and then you can rearrange this equation and you can get inner cell is equal to RT by NF log K. And when you substitute this, all these constants like universal gas constant, cell potential, under standard condition is E naught, and so on. You can reaction coefficient, Faraday constant, number of electron n, and all these constant if you substitute in this equation, you will get E naught cells equal to 0.059 divided by n log k. K is the equilibrium constant, and this is nothing but Nernst equation, simplified Nernst equation. Nernst equation is an derivation is important. We can consider a simple reaction like A plus BB. This small a is the quotient of the reactant, and this C is the quotient of the product. And you can write the expression delta G is equal to delta G naught plus RT log Q, and where Q is nothing but the product of the you know, product divided by reactant, that like C, concentration of C cross D, and C is nothing but the activity I already explained. Similarly, you can express like this one. We know that delta G is equal to minus NFE, delta G naught is equal to minus NFE naught, and then you substitute this here. For delta G, you will substitute minus NFE, and delta G naught substitute minus NFE naught plus RT log Q. Divide both sides with minus NF, then this NF gets cancelled. You get E is equal to NF minus RT by NF log Q. And then if you substitute the constant, you will get 0.0257 volt or 0.0591 by N log Q. So this quotient is nothing but concentration of product divided by concentration of reactant, and you can also relate to equilibrium constant or solubility product. So the application of Nernst equation, it helps us to calculate the cell potential as a function of reactant and product concentration. If you know this concentration is 1, then this becomes ln 1 by 1 becomes 0. The entire thing will be 0. Then you can calculate the cell potential will be equal to the standard electrode potential. Like that you can calculate. If you know the concentration, you can calculate the electrode potential or the EMF or the standard potential. And spontaneity also you can determine accordingly. If you know the reaction is given, you can calculate if it is the standard EMF. If you are calculating minus 0.44, you can apply delta G is equal to minus NFE, and based on that you can also say it is spontaneous or not. The half cell reaction you can write, and for anode and cathode you can write, and this value is minus 0.14, and when it is E is negative or delta E is positive, the reaction is non-spontaneous. Already explained that concept. And remember these points when solving numerical, the standard reduction potential of copper. And if it is Cu2 plus 2 Cu, you have to take plus 0.34. But when you are mentioning it as Cu against Cu2 plus 3, it means this is nothing but copper is used as the cathode, which means you can directly take the standard reduction potential. When copper is used as the anode, then you have to change the sign, like from positive, you have to change it to minus 0.34. And then the temperature standard, temperature 25 degree, when you convert to Kelvin, you have to remember the conversion. These three conversion expressions you have to remember. The Nernst equation, and temperature is something other than 25, then use temperature in Kelvin. In our standard unit of each half cell will be given by directly in the equation. So all these things you have to follow key points, then you can work out the angles. And application of Nernst equation, each application you have to explain in detail, but to keep it short, these are the four important applications. The potential of an electron and the EMF of a cell can be calculated if at any temperature and concentration. Knowing potential of an electrode, the concentration of the atom can be calculated, and if you know the concentration of the solution in the galvanic cell can be determined. The pH of the solution can be calculated by measuring the. Okay, the fourth one is the pH of a solution can also be calculated by measuring the EMF. These are the four applications. There are also many other applications like potentiometer titration and many more, which you can also explore. And each application you can give an example and you can explain. For example, the potential of an electrode and the EMF determination. You can write the simple expression of the galvanic cell and then write the net reaction, and then you calculate the cell voltage 1.1. How? Because the concentration of copper and zinc, if you take it as 1, then you will get E is equal to E naught. I already explained in the previous slide. So like that, we try to explain the application little bit, more. If you know the potential, the concentration can be. For example, E naught, E is equal to E naught. Then if you don't know the concentration, you can calculate the concentration like that. If you know the concentration of product, you can calculate the reactant. Like that, it can be done. This is what the third one as well. pH is nothing but E is equal to E naught, minus 0.059 into pH. So the hydrogen ion concentration you can substitute and you can calculate the pH easily. So like that, there are some other numerics. This is another classical example, like iron, uh, iron anode coupled with the Ag cathode, and then you can calculate E naught and E for the cell. So this is how it is done. So I'm not going in detail. This is like a practice numeric you can try, and then if you know the standard reduction potential, you can easily calculate the EMF of the cell 1.24, and you can apply this in the from the Nernst equation. You can substitute everything. For example, iron concentration, silver concentration 0.01, 0.1 into zero point 0.1. Then now you can calculate the potential. I told the other example with the galvanic cell, then also demonstrate with this one. Similarly, chromium, anode, and then nickel cathode. You can also do this. There are several examples you can work out, but I'm not explaining in detail about this one. Similarly, value of equilibrium constant for Daniell cell can be calculated. It's very simple, like zinc and copper one, and this is the Nernst equation, and you can have to apply this log K equilibrium constant 2 into the voltage, that is E 1.1 is the EMF of this one, 0.092 divided into voltage, 37.2, 10 to the power 37.2, it gives you 1.58 into 10 to the power 37. This is also one of the application of Nernst equation, where you can calculate the uh, you know uh, K equilibrium constant. Solubility product. Solubility product is the other one. Dynamic equilibrium between precipitate and dissolved ions will be there, and rate of dissolution will be equal to the rate of crystallization, and you can calculate the solubility product using this expression mx into ay is equal to, it gives xm plus m plus y a minus a m. Like that you can calculate. You can take an example, and you can also apply that in Nernst equation, and you can calculate the ksp, that is um, solubility product. I think with this will finish this lecture. There are other part of the uh, there are some topics in the electrochemistry uh, unit as well. But I think from starting from the basic oxidation reduction reaction, we have covered a lot, like understanding the basic electrochemical cell, what is electrolyte, and how you can choose anode and cathode based on the spectroelectrochemical series, and many more we have seen the, and how their potentials are arranged, and you have to compare with respect to the hydrogen electrodes, and you can choose the standard hydrogen electrode. The potential will be zero, and you can position lithium. We have seen different metal as anode and cathode. How you have to choose? You can choose one from the top and the other from the bottom, depending on the strength of oxidation or reducing strength. You can choose the metals, and you can form an electrochemical cell. Once you form the electrochemical cell, how you can write a cell reaction. You have to write the half cell reaction of anode, half cell reaction of cathode, and you have to write the net cell reaction, and you can apply the Nernst equation, and you can calculate the EMF of the cell. And once you know the EMF of the cell, you can calculate the concentration, and once you know the concentration, you can calculate the EMF, vice versa. And also you can determine the period from the Nernst equation. These topics will be also come in the practice, like in the practicals also. You will be applying the Nernst equation in the potentiometric calculation, and you will be determining the concentration of the ion. So like that we can, there are theory and practice can be coupled. With this I will end this lecture, and in the next lecture maybe I will teach you more about the other topics in the electrochemistry, some reactions or many more which